Okay, I'm doing this video on potential energy for spring, right? Now, I'll be looking at potential energy for spring in two parts, and hence I have named this video part 1, right? Let's begin. Let us say we have a rigid support here, and this is the rigid support over here, and let us say we have a spring, right? Let us say this is the spring. Doesn't look exactly like a spring, right? But I hope it will help you understand the concept. Let us say this is the spring and it is in its mean position, meaning it is neither elongated neither compressed, right? Now when I apply a force to this spring, it will elongate, right? So let me first draw this is the mean position of the spring. When I apply a force to this, it will elongate, so it will take a shape something like this. The spring will elongate and you will have a situation like this, and let us say this is it, right? So this is the elongated spring on application of force. Let us say the force applied is F over here in the downward direction, and this is the displacement X, right? So we have applied force F and it has caused an elongation X. Now this particular force has deformed the spring. It has elongated the spring. So we call this force deforming force. So we have a new term, deforming force, right? Very simple. Force applied deforms the spring, called deforming force. Now when I am applying a force F over here, right, this spring is in equilibrium, meaning that the spring is neither getting compressed, that is, it is not neither going back, nor it is further getting elongated. That means it is in equilibrium. That would automatically mean that for this force F, there would be another force equal and opposite to this, which would be set up in the spring. So there would be a force F, I'll call it F dash, set up in the spring to counter this force, because the spring is in equilibrium. And this force F dash set up in the spring is known as restoring force. Restoring force. Right? Why restoring force? Why the name restoring force? The reason is very simple. This is in equilibrium. You have applied a force over here and it is in that elongated position. Now for a moment, let us assume that I withdraw this force, I remove this force. What will happen immediately is the spring will recoil, it will go back, and that is because of the restoring force of the spring. Right? So we have two terms here, deforming force and restoring force. Let's move further. It is observed that this F and X, they are related, and that brings us to Hooke's law. Hooke's conducted a number of experiments on elongation of springs, and he concluded a very simple thing. He said F is proportional to X, meaning deforming force is proportional to the elongation, right? And that is quite easy to understand. As I apply more force, more elongation takes place, or as the elongation increases, more force is applied, right? This will give me the equation F is equal to Kx, where K is a constant and this is known as the spring constant. The value of spring constant is constant for a spring, right? Hence the name spring constant. Let us take some values. Let us say the force applied over here is 20 Newton, and that caused a displacement of, let's say, X is equal to 2 centimeter. Right? I have applied force F, 20 Newton, elongation is 2 centimeter. That will give me, using the formula, F is equal to Kx, therefore 20 is equal to K into 2, and therefore I'll get the value of K as 10 Newton per centimeter, right? So the value of spring constant for this particular spring is 10 Newton per centimeter. And it is good to know the value of spring constant because it is a characteristic property of this spring. From this I can conclude that if I need an elongation of 1 centimeter, I'll have to apply a force of 10 Newton. And the converse also, that if I apply a force of 50 Newton, what would be the elongation? So it is good to have the knowledge about the spring constant of a spring. All right, so we have K is equal to 10 Newton per centimeter in this case. Okay, I'm coming to this end of this video. The objective of this video was to create a background for understanding potential energy of a spring, right? I want to make a last and a final point before I wind up this video, and for that let's go back over here. In this case, the spring was in its mean position. It is neither elongated nor compressed. Now I have applied a force on this spring, right, and it has caused this elongation, right? The point I want to make is this force which is applied is not F. The force applied over here is not F. The force F applied over here is not constant throughout the elongation. It keeps on changing. Let us see how. When the spring is in the mean position, right, I have to apply a smaller force to cause elongation, right? So a very small force, if I apply, the spring will elongate. And as the elongation keeps on increasing, I have to apply a larger and larger force. And finally, To maintain this spring in this elongated position, I have to apply force F. So I want to stress this fact that this force applied over here is the force to keep this spring in this elongated position. To cause elongation, to start from this position 0 to 4, let us say the x is 4 centimeter, right? Let me show it over here. This is 0 centimeter and this is 4 centimeter. And if I break this up into 4 parts, 1, 2, 3, and 1, 2, 3, and 4. Yes. For the first centimeter, I'll have to apply a smaller force. For the next 1 centimeter, I have to apply a larger force because elongation has increased. And for the next 2 centimeters, I'll have to apply still larger force. Finally, I have to apply force F to maintain this in this elongated position. And this is our real life experience also, right? That when we have a spring, let me show it over here. When we have a spring, let us say this is a and let us say there's a spring like this, right? When I apply force over here, it is easy for me to elongate this in the initial few millimeters. But as the spring becomes more elongated, I have to apply a larger and larger force to elongate. And that follows Hooke's law. Force is directly proportional. Deforming force is directly proportional to elongation. So as the elongation keeps on increasing, the force applied keeps on increasing. And so this is the final point I'm going to make in this video, that remember that the force, the deforming force which is applied over here, or the restoring force which is applied over here, is a variable force. It is not a constant force. And we will be using that, or we'll be using that understanding when we look at the potential energy of a spring in the part 2. Right? Thank you.